Okay, so welcome back. Anyway, uh, so today we'll basically get to today's lecture pretty much contains the most important things of computational concern to us in chapter 12. This is uh, basically the thing that we've been building up to, being able to compute certain quantities concerning curves in space or in the plane, which are length, being able to compute tangent vectors and normal vectors to these curves. Okay, and before I go on, I thought I would do a couple more examples like we were doing last time. So here's an example. So say an infinite circular cylinder of radius, say of radius 3, centered on the z-axis, in space in R3. This intersects the plane, say z equals 7, okay, in a curve, right? And what do I mean? I mean that if I consider the infinite cylinder of radius 3 centered on the z-axis in space, and I consider the plane z equals 7 in space, these things intersect in a curve, right? That plane cuts through that cylinder, forms a curve in space, and the thing I want you to do is to find, we'll call this curve C. So find a parametrization for this curve that we're calling C. All right. Now you might immediately pick out what that curve is, right? So if you think about it for a second, if you have a plane, the plane z equals 7, and cylinder radius 3, centered on the z-axis, you think in your head the configuration of this plane and that cylinder, you might imagine what this curve is. Of course, if you're not careful, right, it's not true in general what you're going to say about this for a plane cutting through a cylinder, right? It very much matters at what angle this plane cuts through the cylinder. You're going to get different sorts of curves, or maybe curves that look different, right? So the question is, what is this curve? Well, if we draw a quick picture, right, so this is a 3D drawing, so it can get a little iffy here. What about my infinite cylinder of radius 3 centered on the z-axis? Well, here's my z-axis. A cylinder of radius 3 centered on the z-axis, well, maybe this is its cross-section with the xy plane. But it looks like this, right? Okay, so each piece of this cylinder looks like that, right? Now, of course, the plane z equals 7, maybe that plane is like here, right? And it is horizontal, right, in the sense that it is horizontal with respect to the xy plane down below. It is parallel to the xy plane. So here's my plane z equals 7. And of course, this cuts through this cylinder in this curve, which you might have identified as a circle of radius 3 in this plane z equals 7, right? So that's basically what we're trying to parameterize here, a circle of radius 3 centered on this z-axis, but in this plane z equals 7. Okay, well, how do I do that? Okay, so describing it that way might have been a little bit confusing before you've seen parametric curves, but the way that we can do this, no problem, using this language of parametric curves in space is the following, right? So every point that lies on this curve, right? Every point that lies on this curve must lie in this plane, right? It also must lie on the cylinder, but it must lie in this plane. And what is this plane? This plane, I'm calling this plane z equals 7, but when we say this, this is just shorthand, right? This is really me saying it's the set of all points x, y, z such that z is equal to 7. So regardless of what my points are on this plane, the z component, right, the z slot in any of these coordinates is always going to be 7. Okay, that's the definition, right? So any point, like a generic point here on the plane z equals 7, looks like x, y, 7, right? That's what it looks like. Okay, and so the z slot on this curve is always going to be 7. So I already know what that thing looks like. So if I'm trying to come up with a parameterization for this thing, I may not know what goes in the I slot or the j slot, but I know what goes in the z slot. It has to just be 7, right? Okay. So then how do I come up with what goes in these two slots? All right. Well, I mean, I can think for a second and say, well, what does this circle look like, right? Or what does this curve look like? It's a circle of radius 3 centered on the z-axis here. And this z-axis, if you like, you can think of as being an origin for this plane z equals 7. Okay, and so what do I need here? Really, I'm just talking about the x and y slots, right? So I've already taken care of the height here. So whether I'm talking about the curve here or the identical curve sitting down here, it's really the same thing going on. And so what should I do to parameterize this curve? Well, it's going to have the same parameterization in the first two slots as parameterizing a circle of radius 3 centered at the origin in the xy plane, which we know what that is, or what a parameterization for that thing is. So 3 cosine t and 3 sine t in the x and y slots respectively will work. And of course, this curve, we're not done with parameterization until we write up where our t lives. So t from 0 to 2 pi will get it done. All right. Okay. All right. So this is an example of the sort of question you could be asked to do here, and this is this illustrates where you can use this parametric curve business to explain curves. So let's go in the other direction. Let's start out with parameterization and see what it looks like, or try to guess what it looks like. So again, we're sticking to our cosine and sines here just because that was our first example of a very simple parametric curve. So it's nice to think about this. What about parameterization that looks like this? So let's say cosine t I plus sine t j plus t k. So very similar to what we just saw, except the z slot actually depends on t here. And we'll say t goes from 0 to 4 pi. So what does this look like? Okay. So let's think about what this curve is doing. So here's the x-axis, y-axis, z-axis. Okay, and so when t is 0, where is this thing? So it's at cosine 0, sine 0, 0. So it's at 1, 0, 0, which is like here. Right, so here's 1, 0, 0. Here's where I am at t equals 0. And then as t increases from 0 towards 4 pi, what does this thing do? Well, unlike our previous example where this z slot was a fixed constant, right? In that case, this thing just circled around in that plane, right? The plane defined by whatever the z slot was. But in this case, right, this depends on t, and as t increases, this third slot is increasing, which of course is corresponding to the height here, right? The height in the direction of the z-axis. And so what is going on is this thing rises, right? And it rises around the z-axis and back. right? Where does it get to this point when t is equal to 2 pi? And it continues rising. And this is at t is equal to 4 pi. Okay. So what is this thing? This is a helix. Okay, this is a circular helix. So this is an example of a circular helix, or this is an arc of a circular helix. That has a very, very simple description here, right? Okay, and of course, if you let t just be an r, then you get this infinite circular helix spiraling around the z-axis. Okay. All right. And so this is another nice example. We're going to see a very cool example of something similar much later in the course. When we're almost at the end of the course, there is a very simple trick that we can do here to slightly modify this example to give a really, really nice example of a surface that would be really, really hard to describe in any other way, but you can do it parametrically. So all this stuff that we're doing parametric curves, we're actually going to do later for what are called parametric surfaces, and the move from going to from parametric curves to surfaces is actually not that big in terms of algebraically what you do. Well, I'll just spoil the fun now. You just add an extra parameter. So rather than having a single parameter t, you would have two parameters, say u and v, that would parameterize a surface instead of a curve. Okay, and the analog there works in exactly the same way. So we can talk about surfaces that pass over each other, right? So in this case, we have a curve that passes over itself in some way. Okay, and that's not a problem for us. Okay, so now there's a lot of really, really cool examples of curves, both in space and in the plane, that I will talk about. And this is the part where I said I wish we had even more time, because I could spend a ton of time talking about really, really cool curves. So actually, next time I think in class I'll give you some examples of really, really cool curves, like the tractrix or the catenary. So yeah, there's some really cool curves we can discuss, and we will soon. Like I said, I think maybe next time I'll go in depth on some really cool curves. Okay, so anyway, here is kind of the first thing that we want to do. So remember that there was this business last time. Let me dig up my slide, which is really just a piece of paper. I had this definition of a smooth curve. So we called a curve smooth if it has a smooth parametrization, and a parametrization was called smooth if the parametrization itself as a vector valued function was differentiable everywhere in its domain, and if its derivative was never the zero vector for any t in the interior. And at the end of class last time I showed you why you shouldn't confuse this at all with the notion of having a horizontal tangent line in the case of Calc 1 stuff, because it wasn't related at all to that. Okay, so we're going to see why we have this condition. Now I'm going to add something here. So this was the condition for a curve to be smooth. Sometimes you have a curve that's not quite smooth. So what would a curve that's not quite smooth look like? I gave you I gave you the example. I think I still have that too. Hold on. Do I still have that? Maybe. Do I still have my scribbles? Yeah. So I gave you an example of a curve that's very not smooth. Okay, but of course a curve that's not smooth is not always this bad. Sometimes you have a curve that's not smooth, but it's very close to being smooth. What would a non-smooth curve look like? Maybe it does this. Okay, so it just has a corner, right? Here's another example. All right, and so these are two examples of curves that are not smooth because of a single problematic point, right? So there's a single point that we don't like, okay, but everything else is fine, okay? And so a lot of times you come across a curve like this and you want to do calculus on a curve like this, but you got this problematic point. So what do? Well, you can say my curve is fine except at this point, and so what I can do is I can split it into two curves, right? So instead of calling this the curve C, I would call this two curves, C1 followed by the curve C2. They're connected at one endpoint, right? I do the same thing here. And these pieces of the curve are smooth. Because note that to be smooth, we don't care about this going wrong at the endpoints, right? i.e., at everywhere but the endpoints. When I say this is true for any t in the interior of my interval or domain, that is i.e. Everywhere except endpoints. So it might also be true at the endpoints, I just don't care. Okay, so the point is that to be smooth, it's fine if the bad things happen at the endpoints. All right, that's okay. All right, and so what this means is that we've split this curve into two pieces that are smooth. This is called a piecewise smooth curve. Okay, so a piecewise smooth curve, C, is a curve that can be broken into smooth pieces. Smooth in the sense I previously defined, right? So, for instance, here, right? This curve C is smooth because it can be broken into two smooth pieces. First curve, second curve. Okay. Now you might say, how bad would a curve need to be in order to not be piecewise smooth? Well, you could have like a fractal, right? So you could have this, right? So question: what is not piecewise smooth? Yeah, I mean you could have there's a lot of options here. Let's just say pick the Weierstrass M function. Actually, just look up Weierstrass function. Don't need M function here. Weierstrass function will get the job done. What does a Weierstrass function look like? Well, it looks something like this. And then, so it looks like that, and then you say, okay, well, this doesn't look all bad, right? So you like pick this part, and you zoom in. You're like, if I zoom in there, that looks like that's smooth. But when you zoom in there, what it looks like is this. And then you say, okay, well, maybe I could zoom in like here, and that looks okay. But when you zoom in there, it just looks like this. Okay. And so Weierstrass function looks like this. In fact, it's so bad that it's not even differentiable at any point. It's continuous everywhere. This is continuous everywhere, differentiable nowhere. There's not a single point where it has a derivative. Okay. All right, but it's continuous, so it's a path, right? But it has no derivative anywhere. Okay. So anyway, of course we're not going to talk about things this bad, but the fact that things this bad exist just shows us why in real analysis we can't have nice things. So anyway. Generally, when you have a piecewise smooth curve, all this means is that it's just annoying. You have to break the curve into two pieces and just double the computations you have to do, or break it into 3 pieces, 4 pieces, whatever. That's basically the idea here. Okay, and so going back here, what is it that we might want to do for a curve? So we want to compute the length first of all. Now, of course, if I have a curve defined like a line in space, right, just the whole line, well, that's going to have infinite length because that's an infinitely long curve. So when I talk about length, I'm talking about some piece of a curve typically, okay? So we have a curve that has endpoints, of course. Just quick definition, a curve is called closed if its endpoints match. Oh, match. I put the C after the H. So if its endpoints match, i.e., if you have a parametrization R of t, right? So we're using our typical notation here that I'm not going to rewrite. So I'm not going to rewrite this for the rest of the lecture. And t is in some closed interval, a, b. A curve is closed if r of a is equal to r of b, right? So just in a picture, what this looks like, of course, is here's r of a, and my curve goes out and goes around, blah, 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 and then it ends up back here, right? That's r of b. Okay. Okay. And so, of course, we can compute the length of closed curves. We can compute the length of any of these curves that are finite. Of course, to actually do this, you'll see is kind of a headache because we can only do it in we can only actually do it by hand, I should say, in very special circumstances. But we can always write out the formula for computing the length. So how do I compute the length of a curve? Okay, maybe I lied. I'll write out the full. So length of a curve. What is the length of a curve? So if a curve C has smooth parametrization R of t, which has the usual notation x of ti plus y of tj plus z of tk, and t lives in some closed interval a to b, then the length of C is big L, which is the integral from a to b of the length of r prime of t dt. Okay. That's it. All right. So here's a question. I claim that you've actually seen this before. So if you took Calc 2 at UMD, you definitely saw it. It was like one of the last things you did in Calc 2. But you've seen this before in some way. So where you saw this was computing the length of a curve in the plane parametrically. Okay. So if I write it in another form, if I write this in slightly different notation, then you'll understand what I'm saying here. So if I write this out using this notation, what of course is the length of this? This is the integral from a to b of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. Now, do you recognize this from Calc 2? So in Calc 2, of course, you only had the first two slots, right? So this is what you had instead. But this is exactly the formula for computing the length of a curve parametrically in the plane. Okay, you just have this extra component. Okay, so then immediately you understand why we need smooth. Because this integrand thing, right, is going to get messed up by a curve that is not smooth. Why? This integrand thing is going to be 0. Right? Because remember, our requirements to be smooth was that everywhere in the interior, so everywhere between a and b, r prime of t is not the 0 vector. Well, wherever it is the 0 vector, this length would be 0. You might say, oh, well, what's the big deal if the length of this thing is, if this thing goes to 0 somewhere? So you can try this on some examples. In fact, in your homework that I'm going to assign sometime later today, if I don't get it to it later today, um, it'll be over the weekend, and it'll be due next week. It'll be due next Friday, we'll say. And I'll also, so I'll have your homework due. We'll say I'll have your homework due next Thursday at midnight, and then your first exam will be given to you on Friday, next Friday. So I'll make an announcement about that later. So your first exam will be given to you next Friday, and you'll have over the weekend to do it. More than that, I mean, I'll give it to you on Friday, and then you'll have the weekend, and it'll be due, we'll say, Monday at midnight. So anyway, what I was going to say is that if you actually try to compute this integral for a curve that's not smooth, you'll see exactly what goes wrong versus computing the integral of both parts, right? This is essentially, well, I won't even draw a picture of it. I'll just let you see what happens. I'll assign a problem that has you doing exactly this. All right. So let's do a quick example here. And you're going to probably laugh at the example I do because you're going to say, oh, that seems very contrived. And I will say, yes, indeed, it is very contrived because it is specifically set up to be something that we can compute. Let's do this circular helix, okay? So let's do one arc of the circular helix, right? So example, compute the length of C, which is defined to be one arc of this circular helix. So this is cosine Ti plus sine Tj plus Tk, and T lives in the closed interval from 0 to 2 pi. Okay? So our length is the integral from 0 to 2 pi of the length of r prime of t dt. Okay, so I need to compute what the length of r prime of t is. First of all, what is r prime of t? So r prime of t is, I am taking the derivative of every slot here. So this is derivative of cosine t is minus sine t, so this is minus sine ti plus cosine tj, right, plus 1k. Right, so just quickly checking. Derivative of cosine t is minus sine t, derivative of sine t is cosine t, derivative of t is 1. Okay, and so what's the length of r prime t? Well, now it's just algebra. So this is square root of minus sine t squared plus cosine t squared plus 1 squared. All right. Okay. Well, what is this? Yeah, so of course you should get used to this. Pythagorean identity. Sine squared t plus cosine squared t is 1. 1 squared is 1. So this is square root of 2. Right? Ah, nice. You will see that it's a very nice thing when the length of this thing is constant, right? So the length of this is a scalar. It doesn't have to be the case, right? The length of the derivative of some parametrization could very much not be constant. It could very much depend on t. Okay, but in this case it's constant, so that's really nice. Okay, well, now what do I do? So this thing is constant. That's easy enough. So this is the integral from 0 to 2 pi of root 2 dt. So this is 2 pi times root 2. Right? Because that's just a constant. I can pull that out of the integral. It's the integral from 0 to 2 pi of dt. So that's just t evaluated from 0 to 2 pi, which is just 2 pi. So it's 2 pi times root 2. Right. Okay. So that's cool. All right, so that's the length of that arc of the circular helix. Okay, which, thinking geometrically, right, this is showing you, that if I go once around a circle, then this length, once around a unit circle is just 2 pi, right? But, so then going up a little bit around the circular helix adds this little factor of root 2, okay? So that's one, yeah, you could laugh now at this example. There's even funnier ones that I'll maybe do right now. So here is the more funny one. So this might be, you might think it's funny because this worked out to be a constant, so it's really easy. Let's do another example that's even funnier. So let's compute the length of the curve C, which is sometimes called a twisted cubic. So later on in the course, you're going to have a MATLAB assignment that has you actually plotting some of these curves, so you actually get to see what they look like. So the length or this curve is ti plus root 6 over 2j. T squared j plus t cubed k. Now you might look at that and say, oh, that looks complicated, but actually this factor is nice. For t living in the closed interval -1 to 1. Okay, so I want to compute the length of this curve. So this is sometimes called the twisted cubic. Okay, so there's multiple forms of the twisted cubic. This one is one made amenable to hand computation. Okay. And so, of course, in order to do this, I need to compute the length of r prime. So first I take r prime. So r prime of t is, derivative of t is 1, so this is I. Plus here, this is, so root 6 over 2. Derivative of t squared is 2t, so this is root 6 t j, right, plus 3 t squared k. Okay. Okay. So that's all well and good. Okay, but let's continue. Now I need to compute the length of this thing, so I'll leave that on the screen here. So what is the length of r prime of t? Well, this is square root of 1 squared plus root 6t squared plus 3t squared squared. Okay, and so here's square root of 1, 1 squared is 1, plus root 6t squared is 6t squared. Okay. Plus 3t squared squared is 9t to the 4th. Okay. So then this is square root of what? Can I make this better? Well, this factors nicely. This is actually a perfect square, right? It's a perfect square of what? This is 3t squared plus 1 squared, right? Just check that mentally with yourself here, right? 3t squared times itself is 9t to the 4th. Yep. 1 times itself is 1. Yep. So then the mixed terms are 3t squared plus 3t squared, 6t squared. Yep, that's it. So this is a perfect square. So taking this square root here, I end up with 3t squared plus 1. Okay, so we see that we ended up with a case when the length of r prime of t is not constant. This is typical, right? This is the thing that you're going to come up with more often than not. Okay, so now the length of the curve in question, remember the t lives from -1 to 1 here, so this is the integral from -1 to 1 of the length of r prime of t dt, which is the integral from -1 to 1 of 3t squared plus 1 dt. So remember your power rule for integration, and we can, of course, integrate term by term here. So then what is this? The integral of 3t squared dt is what? 3t squared dt is t cubed, right? So this is t cubed. Okay, what's the integral of 1 dt? That's just t. So this is t cubed plus t, evaluated from -1 to 1. All right. So quickly then, this is 1 plus 1 minus -1 cubed plus -1. So this is 1 cubed plus 1 minus -1 cubed plus -1. That's how we do evaluation. So this is minus minus 1 and minus minus 1. So this is 1 plus 1 plus 1 plus 1. So 4. So the length of that twisted cubic, or that piece of the twisted cubic, is 4. Now, here is the one that you are going to laugh at more. Why are you going to laugh at it? Because notice how this had to be perfectly concocted, that this thing underneath the radical is a perfect square. So the deal with this is that look at what you're taking the integral of. The length here always has this radical, right? And if I just write some random expression here, so if I take a generic parametrization for a curve, and I take its derivative, right, and then I take the length of it, what shows up under that radical can be basically anything. Okay. So it can be whatever. And the problem is that if I give you something like this, if I say compute the integral from a to b of, square root, and I just start writing stuff, right? So 4t cubed minus 17t plus, 37, right? If I write something like this, plus sine of 5t, if I just write some expression like this and say, can you compute the integral of this by hand? Of course, the answer is no. Oh, I'm off screen. So if I ask you to compute the integral like this, the answer is no, you can't do it, because things like this, right, unless it's of a very, very specific form, you just can't do by hand. And so if you actually needed to compute, okay, but the problem, right, philosophically, is that most of the examples you would come across in nature of needing to compute a length using this formula would be something like this. It would be something really nasty. Okay, so then how would you do it, right? If you can't do it like by hand like this, how would you do it? You would use some numerical methods to approximate this thing, because you couldn't, the integral of the square root of blah, where blah can just be some random algebraic combination of functions. In general, you're not going to be able to actually take the integral of that, right? So the way we get by this is selection bias. We only care about the things that are nice so that you can actually do them. Okay, so that's the point. All right, so a couple of things to note. So one, actually, maybe this is the most important thing to note. So even though I said a couple of things here, maybe I'll just mention this one. So one, I previously said that, and I previously showed that a single curve can have multiple parameterizations. In fact, if you're creative enough, you can come up with infinitely many parameterizations for a curve, right? So think of, say, a circle, right? Not only can you come up with infinitely many parameterizations, you come up with infinitely many smooth parameterizations. And so this definition of length used a single smooth parameterization for a curve. So what if I use some other smooth parameterization for the same curve? Will I get the same thing? Yes. So length of a curve is independent of parameterization. So independent of smooth parameterization. So if you are using a smooth parameterization of a curve, if you were to have used any other smooth parameterization of that curve, you would have gotten the same length. Okay, i.e., we get the same length regardless of the parameterization we use. Okay, so this is important, right? Because it would be very, very annoying if we had to come up with a special parametrization that gave us the true length or something, right? So this means that length as concept is as important and as nice as we expect it to be. So we get the same length regardless of the parameterization used. Okay. All right. 2, there is a useful notion of, maybe I should say like partial length. That's kind of conceptually what's going on. And this is via what's called the arc length function. What is the arc length function? No, not functions, just arc length function. What is the arc length function? So the arc length function is, say that I compute, or I have a curve, and my curve does something like this. Okay, so here's my curve. Here's when t is equal to a. So here's r of a, and here's r of b, right? And of course, the length of the full curve, right, is L. So L is the integral from a to b of the length of r prime of t dt. Okay. All right. Now, what if instead I wanted to compute the length up to, say, here, right? So I want to compute the length from r, maybe I'll use a different, let's use a different color. So I don't know if you can see it on that portion. Oh, it barely shows up because it's too dark. Okay, so let's say I want to compute this length here. So not the full length, just the length up to that point. And more interestingly, I want to say let this vary, right? So maybe at some time I compute the length up to here, maybe next time I compute the length up to here instead. So I compute the length up to some like r of t instead. Okay. So in order to compute this length, I define the arc length function. And the arc length function is s of t, and this is defined to be the integral from a to t, right, of, I'm not going to use t here because I just need to use a different dummy variable, so it's fine. So I'll use u. So this is r prime of u du. This is my arc length function. Okay. Now, the first thing to notice about the arc length function is that the arc length function, right, if I plug in b here, right, the arc length function s of b is just the integral from a to b of the length of r prime of u du. But what is that? That's just L, right? That's the full length. So the arc length function where I've plugged in b here is just all of L. Of course, if I plug in a here, it's the integral from a to a of something. The integral from a to a of anything is always 0. Okay. So here's my arc length function here. Now, what is also interesting to note is that defining this arc length function as a function of t allows me to think about things like taking the derivative of this function. Okay, this isn't a vector valued function. This is just a real valued function. Okay, what would the derivative of the arc length function be? So, what would s prime of t be? So I'm taking the derivative with respect to t of this thing, but my variable shows up here in the limit of integration. What magical theorem do you know, right, from Calc 1 that tells you how to deal with this? It had a big name. Right, I'll wait for a few seconds for someone to say it in chat, but so it had a big name from Calc 1. Does anyone remember? FTC, right, fundamental theorem of calculus, that's right. So FTC is the thing that told you how to deal with taking a derivative of a variable. It shows up in a limit of integration, right? And so this says that taking the derivative of this, it's just the integrand with this plugged in, right? So it's just, that's it. And so this is a question that in semesters past, when we actually had uniform final exams, this was a favorite problem to show up on the final exams because it's a neat trick that allows you to compute the derivative of this arc length function, which is kind of a like inherently this seems like a complicated function, but its derivative is very easy to compute. Quick example, right? If I have a curve C, that is, I'm just going to come up with some random, horrible, parameterized thing here. So let's do like t squared I plus cosine t j plus like e to the t k, right? And t goes from, we'll say, 0 to 3, right? So compute s prime of 2, right, where s of t is the arc length function for C. Okay. Well, this isn't so bad, right? So I compute r prime of t, which is 2ti minus sine tj plus e to the t k. Right, derivative of e to the t is just e to the t. So then the length of r prime of t is the square root of 2t squared, so that's 4t squared, minus sine t squared, so this is plus sine squared t, plus e to the t squared is e to the 2t. Right? And so s prime of 2 is just the length of r prime of t with 2 plugged in. So this is square root of 4 times 2 squared, so that's 16, right? Plus sine squared of 2 plus e to the 4, right? Now whatever that is, doesn't matter. That's what I was asked to compute, so I'm done. Okay. All right. Now we only have a couple minutes left, so what I wanted to do in those minutes is define a couple of quantities, and then we'll talk about why those things work out the way they do on Monday. So the next important quantities, this is kind of the last stuff we talk about. So tangent and normal vectors to curves. So this is kind of sort of the pinnacle of what we're trying to do here. There's one more thing that many 241 classes skip over, but I'm not going to because I'm biased and I think it's awesome. So, and that's the notion of curvature. So I will talk about curvature because I think curvature and torsion of curves is like totally sweet. So, so you all are going to be subjected to that, even if other 241 sections aren't. So I apologize, but that's just how it's going to be. Because it turns out that to compute those things I just mentioned, curvature and torsion, if you're already computing tangent normal vectors, it's like one more step. So it's barely anything. Algebraically, you got to remember like one more line. So it's not a huge burden. And so this is the thing that we're really interested in. Okay, so if I have some curve, of course I'll draw it in the plane because that's kind of my interest here. Then I was very interested in Calc 1. In fact, the reason I developed, not I, but Leibniz and Newton, the reason Leibniz and Newton developed calculus in the first place was to be able to talk about tangent lines to curves. So for us, we're going to talk about tangent vector t to a curve at a point. And of course, since this depends on the point in question, the tangent vector is going to be different at different points on the curve. So here, tangent vector is going to look like that, right? And so this very much depends on the parameter t. Okay, but also we want to talk about the normal vector to a curve at a point. And again, this also depends on t because the normal vector here is going to look differently. Here, it's going to look like that. Okay, so this is what we want to talk about. Of course, this is our curve C, and our curve C has parameterization R of t, right? So it's very important to know how to compute these things. This is actually kind of the entire purpose of everything we've been doing up till now. Okay, and so how do I compute the tangent vector to a curve C at a point R of t? Right, so this is computed as R prime of t over the length of R prime of t. Aha! You look at this quantity, you immediately realize it's very important that the curve in question be smooth. Why? Because I'm dividing by the length of R prime of t. Okay, and if that length is ever 0, then I'm dividing by 0 at that point, and that's bad. Okay, and so this is another reason why we need smooth curves. Okay, alternatively, what is the normal vector? And I'll explain why this works out to be normal to t. So the normal vector is t prime of t. So I have to have computed the tangent vector first to compute the normal vector. So it's t prime of t over the length of t prime of t. You might also notice that there is a pattern here. The immediate thing to notice from these two definitions is what is the length of these things? What is the length of t of t? Well, when I take the length, I know that if I have a scalar valued thing multiplying a vector, I can pull the absolute value of that out so that the length of t is just the length of r prime of t over the length of r prime of t. It's 1. Similarly, the length of the normal vector is 1. They have been defined to work out this way. Okay, so these are unit vectors. These are both, this is the unit tangent. So this is the unit tangent to C at the point R of t, and this is the unit normal to C at R of t. Okay, so these are quantities we're very, very interested in. Now, it's going to turn out that actually computing with these does end up to be pretty annoying, even for very, very simple curves, as we'll see. And there's no getting around that, unfortunately. So, unfortunately, and in a way, it's not unfortunate because this is why discussion of curves is so interesting. And I mean, like, you might think that, you know, just thinking about curves, they're one-dimensional things, right? So you might think thinking about curves in the plane or in space is something that was solved hundreds of years ago in terms of all the problems that could be dreamed up about them, but that is very far from the case. So curves are very much still very, very active research area because they're complicated. Like, they're really, really complicated. So as I said, I could spend many semesters talking just about curves. So anyway, we'll pick up here on Monday. As I said earlier, I'll put out your second homework set. It'll be due like next Thursday at midnight. And your first exam I will put out next Friday, and you'll have over the weekend, and it'll be due like not next Monday, but the Monday after at midnight. So and it will cover chapters 11 and 12, as I mentioned before. Anyway, so I'll put that in an announcement later. So when I send out your second homework announcement, I'll mention the exam 1 bit. Okay. So anyway, that's that. I will see you all on Monday. Have a good weekend.